Bismillahirrahmanirrahim. Greetings. In the previous video lecture, I discussed the concept of set. And in that video, I mentioned that there is one-to-one correspondence between the set of counting number, positive integer, and the entire set of rational numbers. It sounds kind of peculiar, counterintuitive, and absurd in reality, but it is again in reality. And there's a seeing is believing. As far as I know from my little knowledge, there is no rigorous mathematical proof for that. There is no analytical proof for that, but there is a visual demonstration that is very persuasive and acceptable. And that's exactly what I'm going to do. I'm going to present that one-to-one correspondence visually, and hopefully will persuade you that is the case. Now, in order to not to make the length of the duration of the video too long, I make this video to be kind of preliminary, introductory, to make you familiar with the terminology that we will be using in next video. Also some elementary kind of calculation that prepares you for the next video. I don't have to do it. Also, I have quite a lot of printed handout that I'm going to put them on. I'm going to zoom it, but except few of them, the rest of them I'm not going to go over them, because you can write the notes or read them. You have the upper hand to your computer to zoom it, and also to pause and write if you write the notes or read it. So there is no need for me to go through every single of them, but some of them I may go over. Okay, then let's start, shall we? Oh, by the way, all of my videos are presented at the freshman college level, but high school students and also liberal art students can also benefit from these videos, and I hope that will be the case. Okay, then let's start, shall we? I have written them large enough so that I don't have to jump back and forth and zoom in and zoom out, and hopefully they are visible to you. And here, the first one is about terms and terminologies that we will be hearing in the next video, and one of them is about counting number, which is about 1, 2, 3, 4, 5, and so on. It's positive integer. I have it. I will show it to you. Then about integers that you are already familiar. Counting number, 0 and their negative, union of all of them. Then fraction also, I wrote it, there are two kinds of fractions we have, proper and improper. The proper fraction is that the numerator is smaller than denominator. We call it proper fraction. Similar word we use for set. An improper fraction is the fraction that the numerator is larger than denominator. We call it improper. And so improper fraction is always bigger than 1. A proper fraction is always less than 1. And when we reduce them, that we can no longer reduce that fraction, we say that numerator and denominator are relatively prime. That's the terminology that we will be hearing also next one, once the fraction has been reduced. And also mention the difference between fraction and rational number, because they are both in the form of A over B, what the difference is. Okay, then, now I also add, because some of them I forgot to mention here, that I have put in extra sheet I have put for them. That is about cardinality, means the number of elements that a set has, either finite or infinite. One-to-one correspondence, as the literal meaning says, there is one-to-one correspondence between the elements of the two sets. And the countable set is the set that you can count the elements of that. 1, 2, 3, 4, 5, 6, 7. You can count every sands in the beach of the ocean. 1, 2, 3, 4, 5. How long it takes is not the point, but we call it countable. And then relatively prime I already mentioned, and reduced fraction I already mentioned. Okay, then let's go now to the next one. The next one is just to make you familiar, counting number is positive integer, and the integers is what you are familiar again. I don't have to go further. Rational numbers, the difference is that the integers, we can put them in 1, 2, 3, 4 in order. We can no longer do that with rational numbers. That's what we use usually set builder notation, not set raster notation, but set builder notation, which means the set of all A and B, where A and B are integers. Again, I have said it in previous video, I do not have to say B is not 0, because if B is 0, we are not dealing with numbers to begin with. Okay, then, rational numbers, we cannot say 1, 2, 3, 4, because between any two rational numbers, there is another rational number. And that can keep going forever. So we cannot say this, the next one is this. There is no such a thing as a next rational number. There is no such a thing as a next rational number to 1. Or there is no such a thing as a next rational number to 0, or so on. Nobody can say that. So they said the set of rational numbers are dense. And then every fraction is a rational number. So the difference is that fraction is a ratio of two positive integers, either proper or improper fraction. The ratio of two positive integers, whereas rational number can be positive or negative. So that's the difference when you hear the word rational, when you hear the word fraction. Okay, we are done with this. Let me go on the back of that. Sorry for the primitive equipment I have. Hopefully, inshallah, someday soon I will have a good institution that I could use their facilities. Maybe they hopefully have a smart board and I can accommodate some animation and make it more kind of fancy and enhance it better. Okay, now this, I already mentioned that one, fraction is a part of a whole. This one I also mentioned. Now let's go to these two numbers. Every rational number has two equivalent forms. I didn't say equal, I say equivalent. So every rational number has two equivalent forms. One of them is in the form of A over B, where A and B are integers. And second one is decimal representation, which we divide denominator into numerator, or numerator by the denominator. We get the decimal representation of them. Now, for instance, you see 1/3, two representation of the same decimal number. One of them is in the form of A over B, and the other one in the form of decimal representation. Now, the decimal representation of a rational number always has a repeated pattern of digit or digits. Sometimes the length of the digits that they start to repeat could be 10, 100, 1,000, million even, billion. Now here only one digit is repeating, 3, 3, 3, 3, 3. Could be two digit repeating, like 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and so on. Or could be 10 digit repeating, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then again, 1, 2, 3, 4, 5, 6, 7, 8, 9. I said 10 digits is 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. Now, if it is 1, 2, 3, 4, 5, 6, 7, 8, 9, then what is the A over B form of that number? We are going to learn it, which is very simple, junior high school level. It's not complicated mathematics. Okay, so this one we are finished. This one I have already written for you. The decimal in this is equal to 2/3. We are familiar with them, we have learned. Now, let me see. Which one will be next? Now, let me talk about our number system, which is a based on place value system, and briefly talk about that one if I may. Now, our number system, which is Hindu-Arabic system, based on place value system, which means place of the digit, the column that digit falls, determines the value of the digit. For example, if you have 11, 1 here means the value of that digit is 10, and the other one, both of them are skinny ones, both of them are 1, but the one that falls in this column has the value of 10. The other one, which is a skinny like first one, no difference, falls in the unit column, has a value of 1. So this one has value of 10, this one has value of 1. This one has value of 100. If you have 111, 1, 1, 1, all of them are a skinny one, but the one in here has value much higher than this, 10 times bigger than this, the value, and this has 10 times bigger than this, the value, larger than this, it's bigger than that. Okay, now, what does 0.3333 means? In other words, we know that the limit of that, it keeps going forever as a matter of fact, the limit of that is 1/3 of a whole. What does that mean? In base value, based on place value, that means 0.3, then 0.03 added to that, then 0.003 added to that, then 0.0003 is added to that, as I mentioned, and that keeps going forever. So there is always a little point, 0.0000 whatever 3 is added to the previous one. It's a nice looking sequence. When you go to series and sequence in calculus, you will be seeing this stuff coming up, very interesting and explained much better. Okay, now let me see if I have anything on the back of this. Yes, I do in fact. Okay. Okay, here we know that 1/3 equals 0.333. I already went over that. Now, assume that we don't know. Pretend that we don't know. So I covered this one, and then see how we can come up by knowing only 0.3333. Can we get the other equivalent form of it, which is what? In the form of A over B form of it. They are equivalent. Let's see, let me, as a matter of fact, I have something here. Let me cover it so that we pretend we don't know the answer is 1/3. Or let me even write, let's say n equals to that, x equals to that, y equals to that, or a equals to that. Let's say n equals to that. Now, if n equals to that, then negative n, you just multiply both sides by -1, is that right? Or in Word, you can say, so you multiply both sides by -1, then because the digit, one digit only is repeating, so you can align it. So if you multiply that by 10, the decimal unit will move 1 unit to the right. Is that right? And when you do that, the rest of the decimal, look at that, they align each other, under each other. So if you subtract, they cancel each other out. It's very kind of creative for the grade school student can do that, or a junior high, give him the feeling that is nicely you can do all of these. Okay, so I multiply this one by negative and add to that, or I can say subtract negative n from 10n. What is n? I just don't know. I just let this to represent n, whatever it is. 0.3, then 0.03 added to that, then 0.03 added to that, keep going forever. So let n represent it, whatever it is. Now I do some algebraic manipulation, and I find out what is the n is. Abracadabra, very nicely. Okay, then I subtract n from 10n, I get 9n, and this decimal, they all start to cancel each other to 0. So I'm left with 9n equals to 3. Again, algebraic manipulation, divide both sides by 3, by 9, excuse me, I can find that. So n equals to 9 over 3, 3 over 9, what I'm talking about. 3 over 9, and as I said already, we want the fraction to be in reduced form, which means numerator and denominator to be relatively prime. So we write it in reduced form. And instead of writing 3 over 9, we write 1 over 3. We reduce that one. This is called reduced form of the same fraction, 3 over 9, and also you can say numerator and denominator are what? Are relatively prime. Okay, let me see if I have the back part of that I have already gone over. Now, let me see another example just for the sake of it to gain kind of more muscles. And this one is the n is not 0.3333. I just select number like 41.22222 and so on. So let's see what is the a over b form of this. Don't forget that this 0.2 keep repeating forever. So from the previous example, we learned the art of multiplying both sides by something so that the repeated digit or digits, they start to align each other. Unfortunately, we cannot do that for irrational numbers. But because irrational numbers, they don't have a pattern of repetition. That's the beauty of rational numbers, that we can do that. Okay, 2 ways we can do that. If you like to stick with the 0.333 that we covered in the previous example, just ignore 41, cut it off, keep it aside, and then work with 0.222222 and so on, and find the a over b form of that. The a over b form of 0.2222 and so on, and then whatever it was, add it to 41. Huh? Common sense. Now the other one that I went through that directly is that I said, okay, if I multiply this one by what? By 10, the decimal point will align. You see that? So I say, okay, let's multiply this one by 10. I get 412.222222 and so on. And the n is 41.2222 and so on. So if I subtract n from what? From 10n, which I did that, and I multiply both sides by negative, I add them together. So what do I get? I get negative, and I take n out of 9, out of 10n, I get 9n equal to, you see, they all cancel each other, and 41 less, well, 412 less 41, I end up with 371. And again, very simple algebraic manipulation, n will be equal to 371 divided by 9. Now this is what improper fraction, because numerator is bigger than denominator. Now, denominator is divided by 3, divisible by 3, but numerator is not, because summation of the digits are not divisible by 3. It's 4 and 11. So this is numerator and denominator already are in what? In relatively prime. You cannot reduce them further. So I will go, these examples come up in the next video that I'm going to discuss after this. Okay, do I have anything else? Not really. No, what else I have here is a lot of print out very nicely, and I will zoom them, but most of them I'm not going to go over them. I leave it for you to write it or to watch it, or if you don't need it, you just pass it. But 1 or 2 or 3 of them is good, I may go over them and explain to you further. So let me hang them and then go and zoom it so that is will be readable to you. I will pause for each of them so that you can read them, but you also have a privilege with the computer that you can pause it yourself and even zoom it, and then write it or read it, and then pass to the next one. They are very informative, good to know. Okay, finite and infinite set. I pause a little bit and pass it. One or two that they are kind of possibly important, I will mention it. Infinite set. Again, hopefully it's visible for you. I did zoom it for you. Okay, next. Countable set. I already mentioned what that means. Set that you can count the elements of that. Set of real numbers you cannot count. And I will also go over that for you in the videos to come. Countable set. Okay, next. Set of natural numbers. Now in this handout, I have shown that there is one-to-one correspondence between a set, and even if you take one of the elements of that out, it doesn't make any difference. As a matter of fact, that was possibly the motivation for Hilbert Grand Hotel. So first one single guest comes, and the manager opens room for him, even though that was already filled up. But anyhow, I may also make a video about that. But internet, YouTube has very nicely animated that. I'm not that much skillful for that, so maybe it's even better to watch that one rather than I give you a lecture about that. Okay, then as you said, the set of natural numbers is there is one-to-one correspondence, even though one of the members of the set of rational numbers are taken away. Now, even if you take finitely many of them away, again there is one-to-one correspondence. So it's showing only one to kind of motivate you, to give you motivation. Okay, next one is that is counterintuitive and peculiar, absurd in a sense, that there is one-to-one correspondence between the set of natural numbers and the set of odd integers. The set of all positive integers and the set of odd integers. But the set of positive integers already include the set of odd integers. So it looks like the set of odd integers should be half be as large as set of counting or positive integer, but end up to be they are same. They have same number of elements. They have same cardinality. Again, it is intuition, but there is seeing is believing, so there is a very nice demonstration for that. That was first presented by Cantor. But in reality, Galileo Galilei has already talked about that for a few hundred years before Cantor became interested in that. But that is the history. So the cardinal number of the integers, here it is the set of integers, positive counting number, negative counting number, and 0. Now we want to show that there is one-to-one correspondence between the counting number and entire integer. Looks like the set of integers should be twice as big as the set of counting number, but end up to be the same. They have same cardinality. Again, counterintuitive, but seeing is believing. Okay, let me now show that one. And I also have mathematical formula for that, which makes that one much stronger. Look at that. 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Counting number. Now let's look how he pairs them. He said that let what is it, the even integers to represent what positive integers, and odd integers represent the negative integers. And then you can put one-to-one correspondence between them. You see, 1 goes to 0, 2 goes to 1, 3 goes to -1, 4 goes to 2, 5 goes to -2. So you can say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and so on and so forth. I start to count them. 1, 2, 3, 4, 5, 6, 7. Of course, it takes forever, but the one-to-one correspondence is perfectly persuasive. You can see that, huh? And here I have also written the mathematical formula for that. I don't know if you can use induction to prove it mathematically. This is the case. Okay, interesting, is it not? That's the beauty of mathematics. The world you go for no man has gone before. That's what you go with mathematics. Okay, now let's go to cardinal numbers. Again, same thing as I already covered, but this one I'm going back and forth through circle, and hopefully you will see them nicely. Okay. Again, you have the privilege of stopping your pausing and writing or watching or reading it in more detail. Now, infinite set, I'm saying that countably infinite set or countable set, there is also a name that universally they use it, they call it alif, which is, alif is really first word of the Arabic letters of alphabet. So we can show that between set of counting number and even integers, there is one-to-one correspondence. Same is true between them and a square, or perfect square, like 1, 2, like 1, 4, what is it, 9, 16, 25, and so on. There are infinitely many of them, and there is one-to-one correspondence between set of what? Set of counting number and complete square, which means we can count them. We can count, this is first, this is second, this is third, this is fourth, and so on. And Fibonacci number, and also any infinite subset of a counting number, any infinite subset of that is also what? Is also countable, if the set is already countable. So that about this. Now, I guess that's it. I have two historical background to say, but I will leave that for the next video, and I will zoom it on for you. Okay, then let me zoom it for myself so that I say a few more words, and then that will be the end. Okay, then I will be, again, I repeat myself, I will be uploading one more video demonstrating the one-to-one correspondence between the counting number and the set of rational numbers, which is, again, I repeat myself, is counterintuition and is kind of absurd, but seeing is believing. Okay, then I thank you for watching. I wish you all prosperity, and please stay safe. So long.